So it might appear that Dirac had solved the problem of quantum mechanics, combining quantum mechanics and relativity. But note that Dirac's solution only works if the particle in question is a fermion, that is a spinor. But we do have particles in nature which are bosons, and therefore they have integer spin. And such particles, what would be the equation describing such particles? A picture like this would not be applicable for such particles because, as we know, that a boson in a given energy level, you can have an infinite number of bosons. So, we could not, fill up all the negative energy states with bosons. So that's one of the reasons why, even though this quantum mechanical picture is very compelling, it doesn't actually work out in the end, and that we need quantum field theory. So that's, say, one of the conceptual challenges is that this doesn't work for bosons. So another conceptual challenge is that in non-relativistic quantum mechanics, we treat time and space asymmetrically. Time in the non-relativistic Schrodinger equation is just a parameter, whereas space is actually an operator. And in the Heisenberg picture, the position operator can be a function of time. So when we go to a relativistic setting, we have to treat time and space on an equal footing. That means that we have to demote space for the position operator from an operator to just a coordinate. And that's actually the path that is taken by quantum field theory. Of course, we could have gone the other way, where instead of demoting the spatial coordinates to, say, demoting the spatial coordinates to being just a parameter, we could have promoted the time coordinate to be an operator. So, but then the question is that what is the parameter which would take the place of time? Because in physics we are trying to predict the future, so we need to parameterize time with some parameter. So the obvious answer to that is the proper time. So then in that case, time and space would be functions of proper time. But proper time is not a unique time. You can always, consider a function of proper time, and as long as the function is a monotonically increasing function of tau, f itself is equally good as a time variable. So such a theory should explain why we would have such a redundancy in the description of time. This sort of redundancy is called a gauge freedom. Now, one could imagine that these space-time coordinates, let's write them the x mu, is not just a function of proper time, but there is another coordinate, say sigma. In that case, what one would be describing is not a relativistic quantum mechanics of particles, but a relativistic quantum mechanics of strings. And in fact, string theory takes this route. So even though in quantum field theory we don't take this route of promoting time to an operator, I wanted to say that it is possible to do that, and actually the results that you get are completely consistent with the way that quantum field theory deals with it. So let's close by some concluding remarks. So the idea is that the most important lesson we have is that the combination of special relativity and quantum mechanics is that the number of particles as well as antiparticles is not fixed. The other comment that I wanted to make is that non-relativistic continuous system multiparticle systems can also be described by quantum field theory, And number three is that, in quantum mechanics, we observe that, integer spin particles satisfy Bose statistics and half integer spin particles satisfy Fermi statistics. However, this is something that you have to put in by hand in quantum mechanics, but in relativistic quantum field theory, this is a theorem. The theorem is that if you have particles with integer spin, they must satisfy Bose statistics. And if they have particles with half integer spins, they must satisfy Fermi statistics. And this is known as the spin statistics theorem. And then the last comment I want to make is that quantum field theory and the description in which both space-time become observable, then they have the same predictions, but the quantum field theory approach is easier to deal with particle physics, whereas the other approach is easier to deal with string theory.